recording. All right, so good afternoon. Welcome to the class again, to RC Design. So let me just repeat. I have discussed with Dr. Sneed, we're not going to have the last homework graded. We're going to leave the homework for you to do it yourself, and we'll send you the correct answer so you can double check, cross-reference. And with that, I think we'll finish all the assignments and exams before the finals. So if you want to calculate your grades, it's very simple, right? You take 25% of the quiz plus 12.5% multiplied by the quiz grade, 12.5% multiplied by the homework, and 25% the first exam, 25% multiplied by second exam. You should have a grade, and you will know how much you need to get to the corresponding grade you wanted. Okay. So there is attendance and other incentives. I think most of us are okay, and that reflect through the quiz, and you will find out if you're not receiving the grade. I'll let you know. I'll probably email you already if you absence too many classes. All right. But beyond that, I think we're ready for the final after finishing today's class. And a little bit more information on the final. The final is going to be online. Okay, so pretty much the same format we have done for the first and second exam. And about the length of the exam, I had in my head that we're going to have about 1 hour of duration. Again, we'll make more time for you guys, but I'll finalize that with Dr. Sneed next week and let you know. Okay. So that's about the homework grading and final exam. Before I get any started, any question on these?
Yeah, I had a question actually.
Yes, sir.
Do any homework or quiz grades drop?
What do you mean by drop?
Like, do you like drop the lowest score, like take it out of the grading?
Uh,
Or
I don't think so. We have quite a bit of quiz and homework, right? I mean, I believe I think we have about 8 or 9 or 10 quiz and about 10 to 11 homeworks. So 25%, that's really not a whole lot. So I don't see that the homework quiz will have a significant impact on that, unless you miss a lot of quiz and homework.
okay,
Okay,
no, I didn't. I was just
right.
wondering.
Right. So I don't think we'll do the drop. I don't think that's the case on the syllabus, and I'm not going to enforce that. Is that does that answer your question?
Yeah, that's fine. I was just
Okay,
wondering. That's
sure.
cool.
Yeah. Anything else, folks?
I had a question, Professor.
Yes, sir.
So, did you say the next, like, and there's gonna be additional homework after homework 10 that's not graded, or is homework 10 the homework that's not graded?
The current homework on the development lens, which is due today, will be graded, but the next homework supposed to be on the column analysis will not be graded. I haven't posted yet.
Okay.
Yeah.
On the grade book, it shows homework 10 being out of 0. So I was wondering if that was just a mistake.
Uh, I think that's a mistake. We haven't finished. I mean, we haven't got all your submission yet. I think it will be graded by the grader, and we'll give a grades on that.
All right. Thank you.
Yeah, sure. Anything else, folks, about the homework and about exams? All right. Okay. So let me get back to the course content. It's going to be relatively short today. We don't have a whole lot left for the column analysis, but still we have 3 or 4 steps. I'm going to go through them. Okay. So let me show this. All right. So let's continue and quick recall what we have done so far on the column, right? So this is the critical figure or critical diagram you will need for the final exams. Now, if you in the middle of the exam you forgot what we're going to do and what we're supposed to do, at least draw the shape of a diagram, and I can give you partial credit for it because this is quite important. Okay. So what we're trying to do is we're trying to get point A, B, and C, and D, and E, and finish this interaction diagram, and then you can build your design diagram based on this. I don't think we have time to reach the design part, so for now we're just going to go do the analysis. But from these points, you can see that point A, we talk about this, is the pure axial load. That means there's nothing but axial force, right? So for the pure axial load, how to compute that, we haven't shown anything, right? But this is actually the equation how to compute the axial force. It's actually at the beginning of the lecture, right? So right here, this is the pure axial load, P naught. Okay, it's very straightforward. You just have two part, one part from the concrete and the other part from the steel. All right, and there's a reduction factor, don't forget, 0.85 in front of the concrete portion. Okay, so that is the point A, pure axial force. Okay, then we scroll down the curve, and next point is point of zero tension, and next point is balance failure. And we have a tension controlled limit, and we have the small compressive zone point. And all these points, as we discussed last time, were controlled by the strain and the tension side of the reinforcement. Okay, so essentially it's saying that depends on the strain at the tension side of reinforcement, you will have a strain distribution, and you can judge which points you're looking at, or which stage you're looking at. And again, by these points, right, we can divide the whole curve by three stages or three zones, right? We have this compressive failure zone, which we have a phi equal to 0.65. We have the C to D, which is the transition zone, and we have a varying phi, and we have a D to E, which is the tension controlled limit, tension controlled zone, and in this zone phi equal to 0.9. All right, so these just the corresponding strength reduction factor you need to use to get the strength or capacity. And we talk about how do we do the axial forces and bending moments. And we have the equations for them. So these are the moment and those are the axial forces. And then coming back here, we showed the example in last lecture, end of last lecture, that we have a section like this, and width is 12 inches, height is 20 inches, bars and 2.5 inch apart from top and bottom fiber of it for number 9 bars. And we're trying to find the solutions to the 4 questions here, okay? First one is to find the force, axial force and bending moment corresponding to the balance failure, which means point C. All right, so we have gone through that, right? First, we'll show the strain distribution, the stress distribution, and the internal forces, right? So for the strain distribution, we know that the concrete is going to fail at 0.003, so that's a constant. And then we show that from the Whitney stress block, you can actually get the compressive zone C and get the compressive zone, effective compressive zone A, and then we can compute the stress distribution, right? And that's what we did. So this is 0.003 of a compressive failure strain, and I assume it's going to yield because I have a balance failure, right? So this is balance failure, right? It's balance failure, so I know that my tension reinforcement will yield, which have a 0.00207 of strain. So with that, I can compute my actual compressive zone C equal to depth multiplied by this, and this is the ratio between the strain in the concrete and strain in the concrete plus the tension strain of the steel. And I can find my compressive zone 10.3 inches and use the beta-1 Whitney stress block equation. I can get my actual or effective compressive zone 8.76 inches. All right. So with all this, now I can start doing the stress for the reinforcement. Now I mentioned for the tension reinforcement, again, notice it is balance failure, right? Balance failure means the steel yielded, and it's grade 60. So I know that my tension stress for the steel is 60 KSI. All right. Now for the compressive side of it, I have to run the trigonometry, the triangle here, to compute what is the strain in a compressive reinforcement, right? So I plug in this number and get the strain and multiply the Young's modulus of steel, which is 29,000 KSI, and obtain the stress in the compression side of the reinforcement, right? Compression side of the section. And turns out this number is bigger. It's a 65.9 KSI. It's bigger than the yield strength of the steel, right? Now we talk about this in the beam design section. We said now the bar does not allow to be yielded in a compressive region, right? So we said that, but this is the column, right? So columns mainly in compression, hence it is allowed. So F prime S, when it's bigger than 60 KSI, you can set it as 60 KSI. All right. So in column design, we do allow compressive reinforcement to yield. All right. So remember that it is allowed. Okay. So with that, we bring in and find out the compression force from the concrete is this much, and compression force from the steel this much, and then tension from the steel is this much. And then to get the total compression force in the section and bending moment, we did a free body diagram, right? We make a cut on the column, and the blue ones are the external forces and the purple ones are the internal forces. So the external has to equal to internal, right? So we do the axial force and we got this axial force to be this much. And we do the moment, sum the moment, we got the external moment P multiplied by E, which E is eccentricity equal to the moment from the internal forces. All right, and then we plug the number, we got the compression force to be 350.2 kip and moment to be 310 kip foot. And we can obtain my eccentricity equal to the moment divided by the axial force, and turns out to be 10.66 inches. So every time you want to calculate the point on the interaction diagram, you always need the three numbers: axial force, bending moment, and then the eccentricity values. Okay, so this kind of cap question number one, right? Question number one. Then recall here, question number one is trying to find a P and M and E corresponding to point C, right? Point C is the balance failure. So point C is right here. Okay, point C right here. All right. Then the second question is asking in respect to the tension failure region. That is to pick a point between D and E. Pick a point between D and E. Okay, so let's continue and trying to pick a point between D and E. So to visualize it, I always, every time I'm trying to solve the problem, okay, so let me get this to be blue. So every time I'm trying to solve the problem, I try to visualize where they are in terms of the interaction diagram, right? So now in the interaction diagram, it looks like here's like this, and then here is the P naught, which is the point A, and somewhere here is point B, zero tension point, and point C is here, the tip, and D is somewhere here, and E is somewhere here. Now this is just a conceptual, right? I need some numbers, right? So for C, I know that epsilon S equal to 0.00207 for grade 60, D epsilon S equal to 0.005. All right, so with this drawing in mind, I'm thinking about question number two is to find a point, basically is to find a point within D, E, right? To find a point somewhere between this region. So I'm just gonna highlight it, and basically to find a point in this region. Okay, this color is not good. Let me try a different one. Okay, not better much, but anyway, so it's trying to find a point in this region. So which point should I find, right? So I need to pick a point here, basically, right? To find a point here. So what does it mean, right? This simply means I need an epsilon s that is bigger than 0.005. That's all I need. Epsilon s is bigger than 0.005. So which number should I choose? Now, practically, we normally choose epsilon s in this case to be 0.0075, right? And that is the strain and the tension side of the text section, okay? Now, knowing that this is much bigger than 0.005, we know that the stress in the reinforcement has to equal to yield strength. Has to equal to yield strength. So I can utilize that. So I can start compute my, don't forget this is epsilon cu equal to 0.003, epsilon s somewhere here equal to a 0.0075, and bottom section right here. So I can compute my C, which is the compressive zone, using that trigonometry equation, and that is 17.5. So where does 17.5 come from? That is basically the depth of the beam equal to 17.5. Remember, 20 minus 2.5. So multiply 0.03 on the top, bottom here 0.003 plus 0.0075. Okay, and then I can get the numbers out, and my compressive zone side become 5 inches. 5 inches. Okay, now I already know Fs equal to Fy, yield stress is fine. So immediately my effective compressive zone equal to 0.85, and this is beta 1 value. And why is that? Because we have 4,000 PSI concrete. And this multiplied C equal to 0.85 multiplied by 5 inches, and I got 4.25 inch. So that is an effective compressive zone size, right? And with that, I can compute my compressive stress Fs prime. and Fm prime equal to 0.003, and that's epsilon Cu multiplied by 5. This is C, okay? This is C minus 2.5. Why 2.5? 2.5 is basically distance between the top fiber and the compressive bar, right? So this is essentially ds prime, okay? 2.5. Then divided by 5, okay? And then multiply 29,000 ksi, which is Young's modulus. Yes. All right. So with this, Fs prime equal to a 43.5 ksi, and you notice this number is lower than the yield strength of the bar. Okay. It can be bigger, but if it's capped, you have to use 60 ksi. All right. In this case, smaller than that, so we're fine. All right. So that is the compressive stress. Now, talk about the concrete, right? So the total compression force for the concrete is 0.85 multiplied by 4 ksi, okay, and multiplied by 4.25 inch, and this is A, and multiplied by the width of it, 12 inch, right? So the equation is 0.85 F prime C, right? A and B, okay? So now that is 773 kips. So this is the total compression force from the concrete. Now, with that, I can come back to compute the compression force from the steel. So I need the area of steel, AS prime, and I need the stress in that steel at minus 0.85 F prime C, okay? And what is the compressive area, right? I have two number 9 bars on the top, and if you remember, this is my section, looks like this, and I have a 20 in the height, I have a 12 in the width, right? So this is AS, so 2 inch squared multiplied by Fs prime. I just computed is 43.5 KSI minus 0.85 multiplied by 4 KSI. Okay, and with that, I have a number of 80.2 kips. Okay, so that is the total compression force from the steel. Now, from the tension side, TS equal to AS Fy, where AS is the tension reinforcement area, which is 2 inch squared, multiplied by 60 KSI. I got 120 kips, right? Okay, so all the compression and tension force have been accounted for. So I can start to sum my total axial force P will equal to CC, which is concrete, and CS prime, minus TS, tension side. So I have 173 plus 80 minus 110. I got this number to be 133 kips. 133 kips. That is the total compression. All right. To find the moment, right? To find the moment, I need moment. So M equal to CC, and I need half H minus half A, right? And plus CS prime multiply distance, and now this is half H minus DS prime, and plus 120, sorry, TS, which is tension side of it, and multiply distance, which is depth D minus H over 2, okay? And this whole thing is my moment. So I plug the number in, right? So CC equal to 173, multiply half H is 10 inches, multiply this is 4.25 divided by 2, so 2.125 inch, plus compression 80 kips multiplied by 10 inches minus 2.5 inch, plus 120 multiply 17.5 minus 10, and I got this equal to 238 kips foot. So this whole thing have to be divided by 12 inch per foot. Convert a unit. Okay, all right, so now we have the compression, we have the moment. It's easy to compute the eccentricity. So moment divided by force, I have 238 divided by 133. So kip feet divided by kips, I have a foot. So convert again, inch per foot. So I now have 21.5 inch. All right, now this is pretty big. Why I'm saying that is because if I draw the cross section, right, I draw the section like this. All right, and now this is H 20 inches. And now I'm having a column in the vertical direction. Now, if I want to label the force, now this is the center line. This is the center line. So this is the center point O. If I want to label the axial force sits right here, okay, and equal to 133 kips, and have a distance of 21.5 inch. Pretty far, right? So the axial force is already sitting outside the section. Axial force already sitting outside the section. Okay, so this point right here, and remind us, right? So I'm just gonna redraw the force moment diagram. You don't have to redraw it, you already have it, but just don't want to flip the pages again. So I know this is A. Keep practicing, right? A, B, C. You just want to remember where they're at roughly, right? And now this point here is somewhere here. Somewhere here. So on this diagram, I have 133 kips of P and 238 of kip foot of moment and eccentricity of 21.5 inch. Okay, so that is where I am on the moment diagram, on the interaction diagram. Okay, all right, so that is question 2. So I finally got a point that I can have in the tension zone and with these numbers down here. So I keep going, and I say next is to find a point that in the large compressive zone. Okay, in the large compressive zone, right? So compressive failure. Okay, so what do you mean by compressive failure, right? So I mean, what is this compressive failure, right? That doesn't mean that it's in the it's in the pure compression or in the very limited very limited moment, right? So this is very bizarre, right? Where is it at? What is this point at? We need to find out, right? We need to find out. So what we're gonna do is that we know that this is large compressive zone. So I just want to say that C, remember where this is the compressive zone C, okay? C is large, much bigger than CB. What is CB? CB, remember in the diagram, it looks like this. So B means balanced. Okay, it's right here. So whatever compressive zone I have at a balance failure, I won't have a compressive zone bigger than that, much bigger than that. So this is C at balance failure. And this is called fairly large compressive zone, fairly large compressive zone. Okay, so how large is large, right? How big is big? Right? So what we're going to do is we're going to set compressive zone C bigger than the depth of the beam, which is 17.5 inch. Okay, so we can let compressive zone C equal to 18 inch. Now this number is just arbitrary, okay? I just pick a number arbitrary, okay? I just want to have a large compressive zone, right? So with that, C equal to 8 inch, I can have 18 inch. I have effective compressive zone A equal to 0.85 multiplied by C, and that is 0.85, sorry, 0.85 multiplied by 18. I have about 15.3 inch of effective compressive zone. Okay, now with that, I can compute my compression force for the concrete, and that is 0.85 multiplied by 4 KSI of a concrete multiplied by 15.3 inch of A, remember, and multiplied by 12 inch. That is the B. So 0.85 F prime C, AB. Okay, so I have 624 kips of total compression from the concrete. All right, now this is from the concrete. Immediately, I want to find out for the steel in compression. So Fs prime, the stress in compressive reinforcement equal to Es multiplied by epsilon S prime. Okay, and now I need to find out epsilon S prime, right? So Fs prime equal to Es multiplied by the equation for it is C minus ds prime divided by C multiplied by epsilon Cu. You have seen this before. Okay, and I can plug the numbers. So this is 29,000 KSI. And bracket inside C, what is my compressive zone size? 18 inches, right? And ds prime, the distance between the top fiber to the compressive reinforcement, which is 2.5 inch, and divided by 18, okay? And multiplied by 0.003. Okay, so the whole thing comes out to be a Fs prime equal to a 75 KSI, which is much bigger than the yield strength of the bar, which is 60 KSI. Now, if this were at the beam section, designed for reinforcement beam, that's not good, right? But in this case, since it is for column, it's okay. It can yield, but it has to be capped at 60 KSI. Has to be capped at 60 KSI. Okay, so in this case, we'll just say, okay, now Fs prime has to be equal to 60 KSI. All right, so I got compression from the concrete. I got a compression from the steel. Well, not yet, but I got a compressive stress. That's as good, right? Now I need to get the tensile strain of the steel, which is epsilon s. I use the triangle equation and swap the corresponding distance and d minus c divided by c. I got this number to be about, sorry, this is 0.003, and this is d minus c. I have 17.5 inch, and minus c, what is my c here? 18 inches, right? 18 inches and divided by 18 inches. Okay, and turns out this number is a negative value, right? Negative value. What happens? It means that my tensile reinforcement, supposed to be tension, right? Tensile reinforcement is no longer in tension anymore. Okay, because we're in a column, right? The tensile reinforcement is no longer a tension, right? It's in compression. All right, and I can actually compute this number out. So Fs equal to Young's mod Es multiplied by epsilon s, and this number to be actually negative 2 KSI. Negative 2 KSI. All right, but because we're dealing with column, hence it's okay for column. Okay, what does it mean? It simply means that I have a what we call it? I have a section that both of the parts from the top and bottom, they have a different stress state, right? They have a different stress state. So the tension and compression swapped. Tension and compression swapped. So on the top side, I have about 60 KSI of stress, and the bottom side I have a negative 2 KSI. Okay, so I switched the orientation of reinforcement in a sense. Okay, but now this does not change the fact that I can still compute my axial force equal to compression from the steel, from the concrete, plus compression from the steel, and minus the compression from the steel. Okay, so I have basically, this is 624. Is it CC 624? Yes, 624. Okay, just want to make sure I have right. Kips plus a 60 multiplied by 2, because I have 2 number 9, minus a minus 2 multiplied by 2. So I'll have 748 kips of total compression force. Total compression force. All right, now I can go ahead and compute my moment using the same equation before, and I don't want to write it, repeat myself, just print the number in. 624 multiplied by 10 inches minus 7.65 inch. Where the 7.65 inch come from? This is basically half A, okay? And plus 120 multiply 10 inches minus 2.5. You've seen this before. And then minus 4, which is the negative force from the bar, and 17.5, which is depth of minus 10 inches. Okay, and this whole thing divided by 12 inch per foot. So I convert everything back to kip foot. So the moment equal to 195 kip foot. Okay, and now with the compression and moment known, I can compute my eccentricity equal to E equal to m over P. So moment is 195, small number, axial force is 748, big number, I got my eccentricity to be a very small number, 3.12 inch. Okay, 3.12 inch. So just want to have a visual, right, where we at. So this is again the section. I'm drawing the side view. This is 20 inches, and then it goes like this. And if I draw the center of this, okay, my P is sitting somewhere right here, with a distance of each eccentricity of 3.12 inches. Okay, now this is very close. This is very close to the pure compression case, right? So if I want to draw it in a diagram, right? This I want to draw in a diagram. So now this is the curve, and then we have A is here, B is here, C is here, D is here, E is here. So this point is roughly right here, roughly right here. Okay, roughly right here. Now you may argue, is it before B? Is it between A, B or B, C? Now think about it. For B, I need to have a zero tension, right? So now I have a compression. So I'm having a point between A and B, between A and B. Okay. All right. So this is problem number 3, and problem number 4, just the pure compression. Pure compression. That means for pure compression, I have compressive zone equal to infinity. The whole section is in compression. Eccentricity equal to 0. So P naught, which is axial force, equal to 0.85 F prime C multiplied by the gross area AG minus the reinforcement area AST plus Fy multiplied by AST yield strength multiplied by reinforcement. Now this is different, right? This is the equation we use for pure compression of the column. Stocky column, right? There's no moment, just the compression. Okay, and I bring the number in here, and this is 0.85, and this is 4 KSI, and I have total area of 12 inch multiplied by 20 inches, and minus 4 bars, okay, and plus Fy 60 KSI multiplied by 4 bars, 4 inches squared. Okay, and now I have a total force of 1,042 kips. Okay, for the pure compression case. All right, so this is easy, right? This is easy. All right, so we have all the points calculated. I want to see where they're at. I want to see where they're at. So I'm going to put them all on this interaction diagram. Okay, so I have my axial force and the y-axis, bending moment and x-axis, where they at, right? So first point here actually is P0, the axial force, and this is 142 kips. Okay, 142 kips. And now, if I draw a line, vectorial line from the origin to this point, okay, and I want to mark my eccentricity. So eccentricity for this case is 0. This is pure compression. Okay, and then the next point, okay, so this is number 4. Next point, number 3, I have P equal to a 748 kips, moment equal to 195 kips foot, remember? And now if I draw a vectorial line here, the eccentricity equal to 3.12 inches, remember? Okay, now point 2 is my balanced failure, right? Remember, it's the tip of my curve, and I have my axial force equal to 357 kips, and my moment equal to 317 kip feet, right? And if I draw a line here, my eccentricity equal to a 10.66 inch. 10.66 inch. Okay, and then a representative of the representative I may messed up the number. This is actually first question, okay? Representative of the tension side, I have axial force of 133 kips, moment of 238 kips, foot, and eccentricity of 20.83 inches. All right, so these are the 4 points that we just calculated. These are the 4 points we just calculated. So to return you the interaction diagram, I just simply have to connect the points. Simply have to connect the points. And this is my interaction diagram. This is interaction diagram. And if I want to miss a point, I didn't calculate this, but this is E equal to infinity. Okay, E equal to infinity. All right, so that's it, folks. All we have to do is, in the exam, we'll ask you a point. You just need to calculate a point and show its relative position on this interaction diagram. On this interaction diagram. All right. So on Monday, I will have a review of how to do a column given a similar problem like in the previous exam. Okay. So please digest what we talked about today and think about it, and we can come back on Monday and continue. Okay. So I think this is a stop point. So I'll stop here and welcome any questions. All right. Folks, any questions?
Hey, Bob. I actually had a question on the homework 10.
Okay.
So what is the difference between 2A and 2B? So 2A is asking extending into the wall, and 2B is asking extending into the beam.
I mentioned that in last lecture, if you remember, right? It's all about the position of the bar.
Okay.
Right. So if you enter in the wall, you have a scenario that I'm just making up the geometry, right? I don't remember exactly what, but assuming you have a beam like this, so this is wall, right? And this is your beam. So you have a bar like this, right? So essentially you're gonna have something like this. Is that right? So if you take a look at the location, right? I'm just drawing the section view, and you have your bar right here on the top, isn't it? So it depends on how much concrete cover you have, right? That you need to determine your bar position factor is a 1.3 or 1.0.
Oh, okay.
Right.
Okay.
So
Yeah,
if it's
so
if it's a
take the whole
beam,
lot.
right? If it's a beam, say now I just have a beam. Right. I'm just trying to draw it. It may look ugly, right? But if it's beam like this, right? So I don't have to do a negative moment. I usually just have a bar goes in like the bottom and hook in like that, right? So I look at the cross section. Now the beam bar is going to be like this, right? And you have to look at the concrete cover again to decide is it 1.3 or 1.0.
Okay.
Better?
Yeah.
Okay.
Yeah. I know you mentioned it yesterday, and I thought
Sure.
I understood it at the time, and then I got to the homework and I forgot it.
Sure, no worries. Yeah. Okay, so try it again. If you still have question, email me, okay?
All right. Sounds good. Thank you.
Yeah, no problem. Anything else?
Can you go up to 0.3? I just missed something when I was taking notes.
Sure.
Right there is fine. Oh,
here?
Yep, right there.
Okay. Okay, so let me stop recording. I think most questions probably